everyone. Welcome and thank you for joining us for the GeoAI Workflows for Mapping and Statistics. I'm Mallory Delgadillo, Esri Product Marketing Manager for our Data and Analytics products, and I'll be your moderator today. Today I'm joined with my Esri colleagues who I'll go ahead and let introduce themselves.
Hi everyone, my name is Omar. I'm the Director for AI Machine Learning. I'm very excited to be with you today.
Hi, my name is Mark Seigan. I'm the Director of National Mapping Solutions at Esri.
Hi everyone, Linda Peters here, working at Esri in business development and primarily focused on working with national statistical offices around the globe. Thanks.
Hi everyone, this is Maher Abdelkarim. I am the GIS consultant in the Public Authority for Civil Information in Kuwait. Nice having you all.
So with that, I'll go ahead and turn things over to you, Omar.
Thanks, Mallory. So I promise you it's going to be a very interesting webinar today. We have a rich program designed for you. And we have an amazing guest, Meher from PACI, one of the leading organizations that's going to show you in action how deep learning is working with ArcGIS to produce production level results. So I'm pretty looking forward to that. This is our agenda for today. We're going to start by an intro for what's AI and machine learning and what AI capabilities do we have in ArcGIS. We're going to tackle the very aspect of why GeoAI for national mapping and statistics. We're going to start focusing on the imagery deep learning capabilities as a big enabler for geospatial AI workflows for these two segments. And we're going to start with a demo. We're going to show a building footprint extraction workflow, an end-to-end demo, followed by the PACI use case. We're going to see how this was put into production with a real customer producing amazing results. And then we're going to have another demo for land cover mapping using deep learning, producing very good results. And we're going to share with you a lot of different use cases beyond overhead feature extraction. And then we're going to close with useful resources and Q&A. So with that said, I want to proceed to first setting the foundation of what's really AI and machine learning and deep learning and all of these buzzwords that we keep hearing, right? So we keep hearing words like neural networks, random forests, cognitive computing, artificial intelligence. And it really boils down to three main categories. So artificial intelligence is the big idea of achieving human level intelligence. And this idea has been around since almost the 1950s, where the term AI was first coined. And then machine learning is one field of AI that's about learning from data to derive rules and extract patterns instead of being explicitly programmed. And deep learning is one specific machine learning technique using deep neural networks, which is becoming very good with dealing with high dimensional data. So computer vision tasks like detecting objects or natural language processing or voice analytics, all of these are making use of deep learning heavily these days. And maybe you're asking yourself, what does this have to do with ArcGIS? In fact, the way we are using AI in ArcGIS is not by building an AI product. We're actually having this as a capability spanning multiple products. So we're having it today in ArcGIS Notebooks, the ArcGIS API for Python, ArcGIS Enterprise, ArcGIS Online, you name it, right? And we are definitely applying research to bring it to more capabilities and products like the ArcGIS Analytics for IoT and Quick Capture and other aspects of the platform. And you can use machine learning capabilities in ArcGIS today to do different things. You can predict geospatial events using the prediction tools that we have. You can cluster vector data to find patterns, like using the space-time pattern mining toolbox, for example, to find the emerging and fading hotspots. You can classify imagery using the traditional techniques that I think a lot of you or all of you are aware of. And recently, you can use it for feature extraction and pixel classification using deep learning. And that's what we're going to focus mostly on today. And GeoAI is the intersection of these two interesting worlds, geo and AI. And we're seeing three main patterns for this intersection today. The first pattern is about object detection and feature extraction. So think of detecting building footprints or road segments or detecting things from streaming videos or drone feeds, any kind of image or video that a human can see things in and detect things under 1 or 2 seconds. We can generally train deep learning models to make this instead of humans if we have good training data. The second pattern is about making predictions, predicting geospatial events like road crashes or water pipeline failures, events that are geospatial by nature, right? Events that have geospatial factors leading into it. And the third is about pattern detection or finding patterns, right? So think of the emerging and fading hotspots or the spatiotemporal multivariable clustering or density-based clustering, etc. And with that said, I want to pass it over to Mark to set the context for why GeoAI with national mapping and statistics. On to you, Mark.
Thank you, Omar. For national mapping and statistical organizations, they're using artificial intelligence combined with geography to enable us to do a number of things. Some of them Omar mentioned. They're doing predictive analysis to identify where occurrences are happening, feature and object detection, visualization of patterns through spatial analysis, for example, clustering of objects to see where concentrations are, and classification for things like land cover, and anomaly detection to find needles in a haystack. National mapping and statistical organizations face many challenges, including expanding stakeholder and user expectations coming from government, industry, non-governmental organizations, all the way down to individual citizens. They're seeing an escalating demand for a broader range of information products, from maps and data to web services and analytics. We're seeing faster delivery of a requirement for near real-time information coming from a large variety of sensors all the way to delivering to many types of devices and apps. We see an increasing demand for better resolution and higher quality data. And we see a growing concern for information privacy. Many national mapping and statistical organizations have had their budgets and incomes cut by anywhere from 25 to 50% in the last few years. This has resulted in fewer staff and overall resources to do the increasing work that's demanded of them. We're seeing shrinking timelines from initial point of data collection, from sensors, all the way to final delivery of information, all of which is required to meet the increasing expectations on these organizations. And as they wrestle with how to adapt to these challenges, there's often a reduced perception of their relevance in parts of government and society. Next slide. GeoAI is one solution national mapping and statistical organizations are turning to. It's enabling us to do more with less. This is increasing our responsiveness by speeding timely information to decision makers. It's increasing our relevance by leveraging technology and expanding our abilities to increase data analysis and information delivery. And this can be done by taking advantage of faster computing with more CPUs, parallel processing, and intelligent neural networks. It's enabling analysis with new GeoAI deep learning algorithms, tools, together with location data. It's enabling us to save time, money, labor, and even minimizing our impact on the environment by reducing fuel costs and emissions and their effects on the climate. We're increasing efficiency and expanding capacity by automating routine tasks, which is enabling us and our geospatial professionals to focus on higher value projects and outcomes, and empowering them to deliver much more information. And finally, improving accuracy and engagement with our user communities, very important. National mapping and statistical organizations have identified their highest value workflows and use cases. We see them prioritizing workflows like change detection of areas to know where to focus their limited resources, and change detection of individual features as they capture these features and update their systems of record. It's used to target feature identification and extraction of those features, to automate the collection of new and changed objects, and to reflect them in this system of record. And last, they're looking at how they use this for analysis and assessment, enabling them to streamline analysis to add value and insights from the data they collect. The priorities with high value to national mapping and statistical organizations include change detection of new or changed roads, buildings, land cover, and then doing the feature extraction of transportation objects for national mapping and census enumeration. We're looking at commercial and residential buildings for national census pre-enumeration and high-resolution national mapping. And using analysis like NDVI to identify changes in land cover for national mapping and agricultural census. So now I'd like to turn it over to my colleague, Omar Mayer. Omar?
Yep. Thanks, Mark. That was a very good context setting for why national mapping and statistics could benefit from GeoAI. And I want to start by saying that the examples are endless. You can think of these use cases, whatever fits with your workflows, whatever you can automate. I mean, Mark stressed on the fact that there is like reduced staff, reduced budgets, and there are higher expectations. And I personally believe that AI is one of the major enablers to make things happen in less time and with higher speed and less cost. And you take all of these examples like agriculture census, building footprint extraction, land cover mapping, detecting change in roads, all of these examples, there is no need or there is less need to do it manually or depend on the traditional methods. With deep learning, we are seeing amazing accuracy and amazing performance as we're going to see today, reaching like 94%, 95%, in some cases 98%, if you spend some good effort and time in preparing quality data. So I want to start by shedding some light on our deep learning capabilities in ArcGIS today. For any of these different projects, if you want to detect something from imagery, you generally need to do three main things or pass through three main milestones. First is preparing data, right? You need to prepare your imagery. So managing your imagery and processing your imagery, building the orthorectified versions of the imagery, etc. So talk about raster functions and image server. And then you need to prepare some training data. So whenever you want to train a model to detect something or do line cover mapping, you need to show it examples of this thing you want it to predict or detect, right? And by examples, we mean like image chips, image examples with labels. And a label here could be like you have an image chip, and with these image chip, you have some buildings. If you want to detect the building footprints, so the label in that case would be the actual footprints in these image chips. So we need like hundreds or thousands or tens of thousands of these image chips to train your model. So we have built some tools to help you with this labeling job. We have a new label objects tool that we're going to show today. We have a training sample manager that you can use for the same thing. And we have export training data for deep learning that can help you export those image chips in a format that's usable by deep learning. The next milestone is training the model. There are different kinds of neural networks that you can use based on the context and based on the use case. But the bottom line is we support all four major types of computer vision deep learning in ArcGIS natively today. And we're going to expand on this in a minute. We have the ArcGIS.Learn module that can help you train deep learning models and do different things related to deep learning in ArcGIS. And finally, there is the inference stage, where you are using and consuming these models to detect something or classify a pixel or classify an object. So think of the three stages in your workflows, and let's have a quick look at the kind of tools under each. Maybe first we need to expand on why we use deep learning in the first place. Deep learning is achieving amazing performance when it comes to computer vision tasks. What you're seeing here is the error rate of algorithms used in ImageNet, which is a worldwide competition for feature extraction and object detection since 2010 till 2017. And you can see that the error rate gradually increases. The average human rate is at 5% in this competition. The error rate that was achieved in 2017 was 2.3%. That's very low compared to the human benchmark. Now I think this competition got stopped because deep learning is achieving very good performance. And that's the reason why we're using it for these kind of tasks. So the applications of deep learning to GIS, think of it as four main buckets or four main types. The first one is about pixel classification. Sometimes this is called semantic segmentation in the context of deep learning. This is classifying the class that classifying each pixel, whether it belongs to class A or class B or class C, right? So think of these are the kind of models that can help you with impervious surface classification, for example. And then there is object detection. This is about detecting the location of these objects in the form of bounding box, for example. And a classical example here could be like counting trees or detecting coconut trees. So we are not detecting the footprints, you're just detecting the location of the object. The third type is called instance segmentation. So in that case, it's not just about pixel classification where you're classifying each pixel. You're actually detecting the object, but then you're detecting the exact boundaries around these objects. And a classical example here could be building footprint extraction, especially when buildings are so close to each other. And finally, there is image classification. Let's say you have detected the building already, and now you want to classify it whether it's commercial or residential. So it's more of like assigning a category to the whole image. This is called image classification. And we can use it for commercial versus residential or damaged house versus undamaged house. So we have all 4 types supported in ArcGIS today. And I want to show you a couple of examples of how we're doing that. So if you think about a typical workflow for deep learning in ArcGIS, it's divided mainly into 4 main pieces. The first one is about labeling data, and you can use different tools for that, or you can leverage the existing labeled data that you have in your system of record, like an existing feature layer for buildings, for example. And next, you need to prepare data for deep learning. So you can either do this from Pro or from a Python environment using ArcGIS Enterprise and Image Server. This is the step where you are generating these image chips with the labels. And third, you can train your model, and you can do this in Pro 2.5 today or using Python API in a notebook environment like ArcGIS Notebooks or your own notebook using ArcGIS.learn. And finally, the step where you are using that model to detect an object or classify a pixel. And again, you can do this in Pro or in Server. So some detail on the specific tools we're going to show today. First, collecting training samples, you can use the new label objects. It can help you draw polygons or circles or squares around specific objects and then export these labeled examples using the export training data for deep learning. So this tool can help you export the chips, and the images are going to be associated with the labels. And depending on the kind of model, depending on the kind of output that you need, you're going to choose your labeling format. Third, you can train a deep learning model using the GP tool, train deep learning model. You're passing some parameters to it, like the raster and the training data, and you get to identify some hyperparameters if you want. And as we mentioned, based on the nature of the task you want to do, let's say you want to only detect objects, like you're only interested in understanding the location of the buildings, for example. So you can use the single shot detector, the SSD, that comes with ArcGIS. You can use the object classification if you want to classify the types. You can do pixel classification with UNet, etc. And finally, you tend to use the models that you have trained, right? So you have 3 different GP tools: classify pixels, classify objects, and detect objects. We're going to see some examples for those right now to use your model across imagery against imagery and find the results. And finally, if you want to have a model gallery to package your model and upload your model to Portal, you can convert it into a deep learning package.dlpk, which is basically a zip folder. And this could be easily created by train deep learning model tool or ArcGIS.learn API for Python. So that's the kind of the end-to-end workflow. Manage imagery. These are the kind of holistic capabilities that ArcGIS provides. Manage the imagery, do the labeling, prepare the training data, train the model, do the inferencing, run the analysis, and do things on top of that. So let's see a quick demo for this. So what we're seeing here is a project where we want to do 2 things. We want to detect building footprints at scale at a big area, as you can see. And then on top of that, we want to classify the type of the building. In that case, we want to classify whether this building is damaged or not. In your case, you can think of classifying buildings as commercial versus residential. So as you can see here, this is a big area of interest. And there are different kinds of buildings here, right? So we're going to start by labeling some buildings. Let's say we don't have any kind of label. In that case, we're particularly interested in detecting the building footprint. So we're going to need to label the footprints. So one thing you can do is to go to the classification tools and choose the label objects for deep learning. You then can create a new class. You can call it buildings, for example. Give it any value. And then you can start labeling, right? So let's take this building, for example. So I'm going to need to label its footprints like that, right? I can choose the polygon. So I have more controls over defining the exact boundaries. So as you can see, I'm labeling the exact footprint, right? And I'm done. So I've prepared a lot of these labels already. You can import this. You can use an existing feature class, or you can do it manually, right? And you can actually have multiple people do this kind of labeling. And then the next step is exporting this in a format that could be used by a deep learning algorithm. So if you go to geoprocessing and look for a tool called Export Training Data for Deep Learning, we're going to find this tool. Two main parameters that you pass here. First is the raster, so I pass the imagery layer that I'm using. And second is the feature class that I've been labeling. So that's what I've been doing here. And then you get to define some parameters. There are some default values for this. The tile size defines the size of the image chips exported, right? And then the metadata format. This is very important. So in my case, I want to use a unit to classify the pixels. I want to classify all the pixels in this raster, whether it's a building footprint, whether it's a building or not, right? So this is more of pixel classification. So in that case, I'm going to choose classified tiles. That's the kind of the format for the training data. Once I click this, run, that's the kind of output I'm going to have. So the footprint training data, you have two folders, images and labels. In images, you have the image chips. And then in labels, you have the specific labels related to the class that each of these pixels belong to. So that's exactly what a deep learning model would need to train. Now that I have my training data, I can start training a model. So if you go to geoprocessing, you can look for a new tool called Train Deep Learning Model. So this tool would, again, take two inputs. The training data, so I'm pointing it to that folder that I've just created, the footprint training data, right? And then I can specify an output folder for the model. So I'm going to make that the footprints model. And then it's automatically going to recognize, based on the format of the training data, that this is training data that can leverage a unit pixel classification. So that's what is automatically recommended, right? And you can tend to define some other advanced settings, right? Like the backbone model, the learning rate, but you can actually use a pre-trained model. That's a very important point. You don't really need to start from scratch. If you have an existing model, you can use it with new data. So that's usually better to start from versus starting from scratch. And then you run that. Once you run it, it's going to take some time based on the kind of GPU that you have. The better the GPU, the more powerful, the better, right? And then let's see the kind of the initial results. How's it going to look like? So the initial results are going to look like this. These are building masks, right? So it has classified these pixels, but as you can see, the results are not that great, right? Actually do that, right? So the results are not that great. They are saying that, hey, there's a building here, but it's not that uniform. And that's why we are leveraging some GP tools to do some post-processing. So for example, we're applying the majority filter, raster to polygon, make feature layer, eliminating some noise, and then regularizing building footprints. So you can see more details about that workflow in a publicly available notebook that we're going to share with you. And after you apply this, these are going to be the clean results that we're going to end up with. So you can see how clean these results are compared to the previous segments. And they are exactly matching the building footprints, as you can see. We can actually see a couple of examples here. Let's go to this area, for example. So you can see here, like, very, very good results. I think the accuracy here was like almost 94%. And let's see another example. So that's another very good example, as you can see. And that's the kind of value of doing deep learning inside ArcGIS. It's not just about training or running a deep learning model. It's about the holistic ecosystem. In that case, we have leveraged the raster functions to prepare the imagery, and then we're leveraging GP tools to post-process the imagery to have these beautiful results. And as you noticed, we didn't use any code in this example. We can do this end-to-end in ArcGIS Pro today. And I'm going to show another example if you prefer Python after the next part. So with that said, I want to pass it over to Linda.
There, hopefully you're seeing my screen now. So I have the pleasure of introducing the case example we wanted to share with you today. I think Omar and Mark did a great job to set up the introduction, but I'm really excited to share with you the story of PACI in Kuwait. Kuwait, of course, on the Persian Gulf bordered by Saudi Arabia. It's a small country, but with great expectations and great plans. So Kuwait actually has a plan called Vision 2035, in which they are looking at growing their country substantially, growing in infrastructure, growing in investment, with over an 11% increase in investment in things like roads and bridges and infrastructure. So that's a big challenge, and it's a big challenge not only for that construction that's going to occur, but also for PACI. PACI is the agency who maintains the authoritative data on those streets and roads, and also produces an app called Kuwait Finder, as you can see on the screen. Kuwait Finder is used today by over 650,000 people in Kuwait, and it is considered the authoritative source. So it's critically important for PACI to keep this information up to date. And not only is it important to keep this information up to date, but do so in a cost-effective and an efficient manner. So with that, what I'd like to do is introduce Maher Karim and ask him to share with us his vision and what they did in Kuwait. Maher?
Thank you, Linda, for the introduction. Today, we are sharing with you our journey with machine learning in order to enhance our productivity as a government agency to update and automate our GIS data. The Public Authority for Civil Information, PACI, established the GIS program back in 2011. PACI is responsible to record all the data about people, addresses, and businesses in Kuwait. Mainframe is our main data repository. All these data sets were linked together using GIS with more than 99.7% of link accuracy. PACI has developed a comprehensive base map for all of the country. This base map is used by more than 170 government, private, education, even individuals in their various business applications. PACI has released a GIS-based public mobile application called Kuwait Finder, which has been downloaded by more than 750,000 users. The state of Kuwait is executing huge infrastructure projects all over the country. Following these changes needs a lot of labor, workforce, and efforts. Coping with these changes needs to have a continuous follow-up, and at the same time, we need to have dedicated resources to do this. PACI is trying to explore and try various tools and ways to keep the GIS data updated. We have decided to explore the use of machine learning and to see how this can help us to enhance our productivity. Machine learning is something new for us, and we need to explore this new field. In order to be realistic, we started to do a rapid assessment about the existing GIS data that we have and that we can use for our machine learning journey. So we looked on the digitized street center lines, building footprints, satellite imagery, and GPS data logs. As you know, satellite imagery plays a vital role to be the source of following and tracking changes in reality. We have access to various imagery data sets like Esri, ArcGIS Online, Airbus 2019, and Airbus 2018. In all cases, these different satellite imagery has different properties, like different colors, different angles of capture, and even different orientation and quality. Quake Finder is another source of truth, as it provides us with anonymized GPS logs that we can use to identify and prioritize areas that need intervention in regards of street networks. Clustering the non-snap GPS can show us where are the areas that our street networks needs updates, and it is an indication to focus our efforts on this data update. Taking all these into consideration, from image, it is not color balanced, it has different capturing angles, different resolutions, not edge match, and missing details, and even it has a poor color contrast. Assessing our vector data, like available street networks and building footprints, we find that we have missing data, or it is incomplete or inconsistent, not uniform. It has center lines, not polygons, and it has data shirts. All this we took it into consideration in our way to apply machine learning. We took the approach of creating our ground truth data, and at the same time establishing a baseline that we can measure to assess how accurate or good the models that we are trying. This is an example of an area that we have created the ground truth for it. When creating around 21,000 features, we needed around 13 days to create this data. We tried to establish and distribute our ground truth data all over the country in order to override the variation of the satellite imagery. We used Airbus 2018 images as our baseline to create the ground truth data. As we mentioned earlier, machine learning is something new for us, and it is a learning journey that we need to take it and grasp all these new terms and technologies. We spent more than 3 months trying and selecting different models and assessing them. We used Mask RCNN, UNet, ConvNet, even we have developed our own neural networks and we named it RoadNet. At the end, we used UNet 152 as our model because it was giving us the best results. After doing the training, we start assessing the data by predicting the output of our models. This is an example of doing prediction for an area around 600 square kilometers. As I mentioned earlier, we trained our model in using Airbus 2018, but we predicted using Airbus 2019. We use this in order to assess how is our model is performing and how much is good to generalize. Running this prediction on this area took around 22 minutes to create a classified raster that can be used for the post-processing. Using the raster image is not enough, because at the end we need to have our data as feature classes representing building footprints, streets, and even parkings. So we have built a data model using Model Builder that take the raster and perform various operations like majority filters, cleaning, buffering, eliminating data, and even regularizing building footprints and classifying the data itself. Running this model over the 600 square kilometers took around 68 minutes. you can see the output of this data. The area after running the prediction and the post-processing, we have generated around 111,000 building footprints and more than 78,000 street segments. This processing took around 1.5 hours, and for sure, we entered it to a visual quality control process, which took 2 days from one person. Doing the same data using manual data entry based on our measurement baseline will take around 119 days, and you can feel the difference. We have implemented visual quality check about the data that was post-processed and produced from the model. Usually, people who are using machine learning are relying on the model training matrices to assess the quality and the performance of the models. But we found that this is not applicable for GIS, because at the end, we need to see the data that was extracted, if it is correct or not. So we implemented visual quality check to go through the data and classify them. How are they correct, or they have, it is predicted correct, but the shape is not correct, or even it is false positive. And this is a matrix for 185 square kilometers of data that was visually checked. And you can see the percentage of the corrected data that was predicted, which reached to 97%. Comparing the output from the data that was digitized by our GIS users and the data which was created by the machine learning. In the left, you can see the user data entry, and in the right, you can see the data which was produced by the machine learning algorithm. And I think it is really, really good. We cannot pretend that we are done. We are still working to enhance our models, our work, and at the same time, our data. At the end, I want to thank my team who really worked and helped achieving this. And we are happy to share our findings, experience with all of you in order to have a common understanding and to be useful for all of the GIS community. Thank you, everyone.
That's really great, Maher. Thank you for sharing. It's just such an amazing story, and you did such tremendous work there, you and the whole team. I just wanted to summarize a bit, if I could, because I think what's really impressive is how much more responsive your agency is overall now. You've not only improved the accuracy in the work that you're doing, but you've saved your organization a ton of time and, of course, money in the same result. And you've also expanded the capacity. So your team now has this new set of skills, which I'm really excited to see what's going to come next out of PACI.
I'm really excited about the kind of results that Meher has shown. It was definitely not an easy path, but I think it paid off. One thing I want to show you real quick is these buildings. As you can see, these buildings are very close to each other. So applying a pixel classification methodology using UNet, like what we've seen in the previous example, might not be the best thing, right? Because we want to be able to separate the building footprints even if they are very close to each other. So for that purpose, we're using another type of network called Mask RCNN. So Mask RCNN is doing instance segmentation. If you recall at the beginning, we mentioned that there are 4 main types of computer vision deep learning. One was semantic segmentation. That's what we have seen in the previous Pro example. And for this one, we're using instance segmentation, which is detecting the objects and doing the boundaries around it. For that, you're going to need very similar training data. You're going to need the footprints, separating each building. You're going to produce your image chips, pass this to a deep learning model. In that capacity, you are going to train a mask RCNN model, and it's going to produce these beautiful results, right? This is, by the way, a publicly available notebook. We have a lot of publicly available notebooks that you can see. So if you go to developers.arcgis.com, don't worry about the kind of lengthy URL. We're going to share this with you. But I want to say that we have a lot of these notebooks here for deep learning, machine learning. You can see the code, and you can play around with it. So I really recommend that you have a look here. So with that said, I want to shift gears to a couple of other things. So first, I've spoken quickly about something called ArcGIS Learn. And I wanted to mention quickly that this is the piece in the ArcGIS API for Python that would help you do different things related to deep learning. One of which is training deep learning models. You can literally train a deep learning model in 3 to 5 lines of code. We're going to see an example for this right now. And you can do a couple of other things. You can prepare the data, export the training data, so prepare the data. So almost everything that we have seen in Pro in the previous example, you can do it in Python, simple Python, using ArcGIS Learn. You can prepare the data, you can train deep learning models. So we have all of these different architectures and models supported to do the 4 main types of computer vision deep learning. We have some model management capabilities, right, to list the model, install the model, uninstall it. Obviously, you have the inference capabilities to use the models, and the list goes on. So in addition to that, you can train your own model using whatever framework you prefer. If you want to train using TensorFlow or PyTorch or scikit-learn, as long as we can interface with these using Python, you can use the Python API to integrate with that. So what I'm saying is you have different options really to train your models. You can use Pro, you can use ArcGIS Learn, or you can train using your custom deep learning framework and do this integration through the Python API. One aspect that I want to highlight is ArcGIS Notebooks. So Jupyter Notebooks is a famous vehicle that help us do machine learning and deep learning and data science in general. We have brought this inside ArcGIS, as you know, and now you have this in ArcGIS Pro 2.5, and it comes with ArcGIS Server 10.7 plus. So we have ArcGIS Notebook Server, you have ArcGIS Notebooks in Pro, and very soon we're going to have ArcGIS Online, ArcGIS Notebooks in ArcGIS Online. And it comes actually with 300 plus data science packages pre-installed, configured, so that you have the beauty of both worlds, right? So we have ArcGIS world accessing the data stores and the analytics engines, and then you have the open source kind of world with all of these data science packages and libraries. So why don't we see an example in action? So I'm going to launch ArcGIS Notebooks. So I have it here. And as I mentioned, if you have ArcGIS Enterprise 10.7 plus like 10.8, you're going to be able to see that. And here you can see obviously a lot of Python code that I'm going to explain. And you can easily add data, right? So you can click add and add data from ArcGIS Online, your portal, Living Atlas, you name it, very easily. And you can add analyses easily, right? So what I'm going to do here is basically, this is a workflow to produce high resolution land cover maps from some labeled data using deep learning. So pretty much everything that I've done in Pro, I'm going to do it here in code. So first, we want to export the training data. We have some area with labeled pixels, as you can see here, and I want to export these into chips. So I'm connecting to my GIS. I'm connecting to the Kent County full label land cover. That's the kind of labeled area that I have. And I'm connecting to the imagery. In that case, I'm using the USA NAIP imagery, right? And you can get this imagery from the ArcGIS world imagery on Living Atlas. You can get this in Pro or Server. And then actually I'm specifying a folder name in the Raster store that will be used to store our training data. And after that, I would like to export the training data using ArcGIS Learn. So I am importing ArcGIS Learn here, and then I am exporting this. So I am specifying a couple of parameters like the input raster, SNAPE, the input layer, the output location, the chip format, the tile size, etc. And then I submit this job, and then I'm going to have these image chips. So you can see this folder here. This is basically what I've produced, right? So you can see these are the image chips, and these are the labels that comes with it. That's what I need to train a model. And then actually I want to visualize the training data. So I am actually doing this. One amazing aspect of ArcGIS Learn is prepared data. It can help you do different things, one of which is data augmentation. So the more examples you can provide to deep learning, the better. And data augmentation is providing more and more image chips with different variations of the original chips. by applying some distortion, for example, and some effects to it so that you end up with more training sets. And then I want to load my neural network. So we're going to use something called UNet, and you can read about UNet more online. And this is the line of code that I'm loading the UNet. So I'm calling UNet classifier, and I'm passing the training data here. And then I'm actually training the model. Before I train the model, one thing that ArcGIS Learn can help you with is finding the optimal learning rate. So the learning rate, think of it as basically the idea of adjusting the weights of the network based on the gradient descent. And this is one very important hyperparameter that needs to be optimized. There are advantages and disadvantages of having a low or high learning rate. So it's not a simple process, but you can leverage the learning rate finder to automate this, right? And then we are training our model in this line of code, model.fit. And as you can see, through different epochs, the accuracy increases. I think after the 10th epoch, we managed to get it up to 94 or 95% accuracy. You can visualize the classification results, the output here, right? And see that it's pretty much matching the ground truth. These are the ground truth versus predictions. That's actually a quick example. So this is the nape imagery, and this is the kind of output, as you can see, and it's pretty much matching those underlying imagery classes. After you do that, you can do a couple of things. So for example, deploying your model to production, have it as an item on portal. So we are actually packaging the model as a DLTK package here, right? And then actually we're gonna add it as an item on portal, and then you can call it and do the inference and obviously have the results. These are publicly available notebooks, as I mentioned. We're gonna share that with you. And this is not the only use case, doing pixel classification or object extraction from overhead imagery. We have a lot of other use cases. So for example, we have been working on parcel boundary extraction, so extracting the boundaries of these parcels. You need a training data of the boundaries of parcels. And if you want to extract the type of the parcel, whether it's agriculture, commercial, or residential, that's going to be needed as an attribute to the parcel boundary as well. So these are some examples for the output that we had. We have worked with, in the agriculture space, on field boundary delineation or field boundary detection. As you can see, these are the input images. These are the labels that we had, and this is an example for the output from the deep learning model. It's pretty good. This could be very useful for agriculture census. Maybe one question you have, what's the advantage of doing this versus the classical kind of supervised learning techniques like support vector machines, for example? The main advantage is in the very way the deep learning techniques work. It applies some sort of hierarchical filtering to understand not only the color of the pixel, but the kind of the shape, right? So it takes this into consideration, and it's generally producing higher performance and higher quality in a lot of the examples that we have used both. So my recommendation is to try out the basic methods first, and then try deep learning and benchmark. So far, we have seen very good results when using deep learning with object detection and pixel classification. There are also some examples of detecting features from oriented imagery, like road signs and reading the text on them. So in that example, we're detecting the road signs, geolocating the road signs, reading the text on them, and we're leveraging some external AI services like the Microsoft Cognitive Services, for example, on Azure in that case. This is an example for the dashboard showing the locations of these road signs. As you can see, you see the bounding boxes here. We've been working on detecting blight, graffiti, and overgrowth from oriented imagery as well. And we've been doing 3D reconstruction from aerial LiDAR. So in that case, we are predicting two things, the building footprint and the roof type. And then we're inferring the height from the aerial LiDAR, and then using the procedural rules in City Engine to come up with this 3D beautiful scene, totally automated without any level of human intervention. We have digitized almost like 500,000 buildings in almost like 2 or 3 hours.
Yeah, Omar, do you want to go ahead and take us away with the questions and the rest of the panelists as well?
Yeah, actually, I might start out with a question for Maher. We've gotten a couple of really great questions for PACI. The first one for you, Maher, is how often does the underlying data, the buildings and the streets change?
Actually, in Kuwait, we are witnessing a lot of changes in reality, but we cannot pretend that we are trying to follow it day by day. In reality, we have it day by day because it is part of our business process for updating this data. But we are updating it on GIS and on the, let's say, on the system of records. But we are trying at the same time to utilize the satellite imagery, because we do not have aerial imagery, to try updating this massive area, because we cannot concentrate our efforts on certain areas to say that this area needs to be updated or the other area needs to be updated. So we need to have, let's say, a high level approach to update the data at least once we have a satellite image, new satellite image, which usually we are trying to get every 6 or 1 year. So we have this data updated, because we have a previous experience of doing this manually, and really it took us 14 months to create only the building footprints layer.
Right.
So having this,
that's interesting, and it actually leads to another question from another listener who asked, have you considered LiDAR?
We have currently a mobile LiDAR project. It is not an aerial airborne LiDAR, it is a mobile LiDAR. We are executing the LiDAR collection, and we are thinking and considering applying machine learning to do the data classification, especially the way that mobile LiDAR is working is totally different than the airborne. So this is, yes, it is considered, but still in the let's say
In process.
in our roadmap. Yes.
Yeah. Well, one more question for you. Sorry, go ahead, Omar.
Yeah, I was just saying that we had a dedicated webinar for feature extraction from LiDAR. If you guys go to that group that I'm showing on the screen right now, you're going to find a post with the recorded webinar video and a link to the presentation. And it's walking you through the different capabilities that you can use to extract features from LiDAR data. Yeah.
Great. I just have one more question for Maher. Again, another listener is asking, are you applying raster functionality to process and prepare the data?
Yes, for sure. For processing and preparing the data, as I mentioned, we have the satellite image covering all of Kuwait, and having this non-uniform extracts of the data all over Kuwait, we need to implement a distributed processing. We are using actually Python and Ray in order to process the raster and extract the masks and label data for these chips. We are not using ArcGIS Pro. We used ArcGIS Pro to do this initially, but the way that we have our data, we prefer to use it using the normal Python tools or even Jupyter notebooks with the ArcPy or ArcGIS.learn functionality, rather using the desktop, because it gives us more space to work and consume the hardware that we have.
Great, thank you. Omar, I'm sure you have some other questions.
Yeah, sure. So we received some questions. I'm going to go through them real quick and answer them right now. So let me do that. Actually, a lot of great questions. So there was a question of how to access the notebooks that I was sharing. So we can access ArcGIS notebooks. If you have Enterprise 10.7 plus, notebook server comes with it for free. If you have Pro 2.5, ArcGIS notebooks comes with it. These are two ways to access notebooks. So ArcGIS notebooks on online is coming very soon as well. So stay tuned. There was another question about, does it matter if I extract the data doing deep learning and transform them to points? So yes, definitely. As I mentioned, there are different types of deep learning computer vision. So we can't detect building centroids, for example, using detect objects like single shot detector. That will help you have the bounding boxes of which you can derive the centroid. Is it possible to use these methods for regression, not only for classification? We have a lot of regression techniques in ArcGIS, like the geographically weighted regression and the ordinary least squares and others. So I definitely invite you to have a look at these tools. What's the difference between deep learning method and simple supervised learning classification? I think we've explained that in the webinar. Is it possible to use AI algorithm for classification on national level? I mean, that's exactly what Meher has shown. Right now, they can do whole Kuwait under 30 minutes versus 5 human years previously with manual digitization. Let's see what other questions we have. Okay. The deep learning model used 3 training models Definitely. So we are already leveraging some pre-trained kind of networks, right? Like ResNet and the likes. So we're not starting from scratch. And in addition, if you have a pre-trained model on specific classes like building footprints, for example, you can still use that. So I've shown in the Pro example how you can use an existing pre-trained model and not start from scratch. So the answer is yes. Okay, let's see. Can we use Living Atlas imagery to extract building footprints for larger area? Yes, we can do this with the world imagery that comes in the Living Atlas. You want to make traffic count data from imagery after, so detecting traffic or detecting vehicles. You can do this from video feeds. We have done that a lot with the CCTV video feeds. You can do it with satellite imagery, but I'm not sure if it's going to help you derive the traffic count because this needs very high frequency, like imagery every hour or something, or even less. And theoretically, you can get this, but it might be a little expensive. So I recommend that you use CCTV video feeds or drone feeds. There is a question about the recommended resolution, and the general answer here is whatever resolution. I mean, obviously, the higher the resolution, the better. That's the rule. But if you want to understand what level of resolution you need, whatever is good for a human being to detect the object or see it under 1 or 2 seconds, usually we can use it for deep learning. So with that said, I want to share with you really quick a couple of resources, and then we can conclude. So I'm going to share my screen again. So we're going to share via email some resources with you, like the ArcGIS.learn documentation and some sample notebooks. I invite you to go to the GeoAI blog on Medium, medium.com/GeoAI for a lot of blog posts summarizing these workflows. And I invite you to join the LinkedIn group on Medium, on LinkedIn. This is the GeoAI group. We're going to have a lot of news, resources, virtual events, and discussions around geospatial AI. And with that said, I want to conclude today and thank you so much for attending. And I'm looking forward to having discussions and sharing your experiences on the group. Thank you so much.
Thank you all.
Thank you.
Thank you. See you.